Okay. So the problem we have here is there's students performing an experiment and they're trying to get a projectile to pass through these rings. So basically, they need to know the trajectory of the projectile as it's launched at an angle of 40 degrees. They need to know the trajectory of the projectile so they know where to place the rings. So they give us some numbers. They give us some ranges of how far the projectile goes at a certain number of trials, and other than that and the angle theta, there aren't really any givens. So the first question asks us to derive an equation for the vertical position of the projectile during the flight. And it asks us to express the answer in terms of physical constants such as x, v naught, and theta. So I'm actually going to move my chain. So the first step here is to so we understand that since the projectile is being launched at an angle theta, we have kind of we have its initial velocity here, or velocity, and however we can break it up into its components. So it'd be like v naught sine theta, and then down here v naught cosine theta, because we can split it up into its x and y directions. So knowing that, we can manipulate the basic kinematic equations to fit our different x and y components. So for example, we have the basic equation. To solve for a, we're going to use two equations. We're going to use delta y, so this is for the y component, delta y equals v naught y times t plus half of ay times t squared. And immediately here I'm gonna replace this with some other stuff. So v naught y can be written as v naught times sine theta, because we multiply to find the v naught in the y direction, we multiply by the sine of the angle, and I'm gonna replace this with g. Yeah. And the second equation I'm gonna use is in the x direction, and that is it's actually the same equation, just in the x form, so it's actually delta x equals v naught, and I'm just going to replace it with cosine theta times t, and then since there's no x or acceleration in the x direction, I'm just going to leave that part out. Okay, so now we have the setup for the equations, and we have a few unknowns. One unknown is delta y, v naught, t, and v naught here as well. However, we do know the angle theta, we know g, we know the delta x because they give us a set of values in the beginning, and they give us theta here as well, so we know those. So what I'm going to do here is I'm going to isolate t for this equation. So I'm just going to divide by v naught cosine, so it's delta x equals t. And then what I can do here is plug in this into each t here. It's kind of long, but it will look something like delta y equals v naught sine theta parentheses delta x cosine theta. So yeah, that's actually, this is the answer to part A. This is the equation that we could use to find delta y at any given point. And I'm just going to erase here. So this is our answer to part A, and we're going to use this later in part C. So the next part is part B. It says, using the data for the range, calculate the launch velocity v naught of the projectile. So I'm going to use one specific value. I'm just going to use the value from trial 1. So it's trial 1, and it turns out to be the projectile goes 8.92 meters. So I'm going to use that value to calculate our v naught. And the way I'm going to do this is we're going to do something similar to the beginning, but before we do that, it's important to understand that at this point here, when the projectile is at its highest, at this point, Vy equals 0 meters per second, and that's because it's at its highest point, so it can no longer go up, it can only go down. So yeah, from there, we're just going to do something similar. We're going to write t equals delta x divided by v naught cosine again. We're going to plug in this t to a different equation later. And we're going to use another kinematic equation, which is usually v equals v naught plus at. However, we're going to modify it so that it says Vy equals v naught sine theta plus gt. And then since at the top of the since at the maximum height Vy is 0, we can just replace this with 0. And then we can plug this in for t. So now we only have one unknown, and it's the same unknown. So I'm just gonna skip a couple steps, I guess. And v naught ends up equaling negative, or actually, g delta x over cosine theta times sine theta. So yeah, basically I just moved this portion over to the left side, so that's negative g times delta x over v naught cosine. Then I multiplied, or sorry, first I multiplied by v naught so that this one cancels out and this one becomes squared. And then I moved it over to the left side, so that's negative g delta x over cosine theta. equals v naught squared sine theta, and then I divided by sine theta and square rooted. And g is still positive because the original value of g would be technically negative since y plus is in the upwards direction, and then it cancels out with the negative sign once we move it. So yeah. And then when we plug in all the numbers, v naught equals 13.3 meters per second. So this is our v naught value. So that's part B. And then for part C, it asks us to find the height of the projectile at a certain distance, 5.13 meters. So if, in this case, delta x equals 5.13 meters, and then we have our v naught, then we can just plug all this in and get the answer. I'm just gonna, so this should be 13.3. This is 5.13. This is also 5.13. And then this is 13.3 as well as this. Yeah, so then it's just a matter of plugging in and simplifying all of this, and then this ends up equaling 3.057 meters, or I guess 3.06 meters. So that's the answer to part C. And then part D is where we move on to the graph and the data table. So they say in part D, it says the students used a video camera to measure the position of the projectile at various points in time. And they basically set up a table showing a set of trials and the specific X and Y locations of the projectile at different times throughout the launch of the projectile. So I'm gonna leave this here. I'm gonna leave this here as well. So basically it's asking us to find a line where the slope can help us find v naught based off the data given. So I'm just gonna make a small table. So this is the set of times throughout the launch, and then this is the distance that it traveled in that time. And then basically, if we think about slope is y over x in a graph. So units wise, to find a slope that would fit velocity, this would be meters over seconds. So basically what I did was I manipulated this equation that we already had so that v naught would equal, or we would solve for v naught in terms of delta x, cosine, and time. So I got v naught equals delta x over t times cosine theta. So basically, we have we have delta x here, we have the list of delta x's here, we have the list of times here, and then cosine theta is a given. So the final variable here would just be cosine theta times time. And then I've calculated those. So it's 0. Yeah, so that's basically it. So in this case, this section would be the x-axis because it's what goes under, and then here, oh yeah, the x in meters would be in the y direction because that's what goes on top. Because if it's like meters per second, so and this is still seconds. So yeah. So yeah, and then yeah, so I'll plot it out really quick. So as you can see, the line isn't perfectly straight, obviously, but it is quite straight. And if we were to calculate the slope of this line, it would come out to 12.51 meters per second. So comparing that to our 13.3 meters per second, to find our percent error, it would just be so our percent error is, oh sorry, it should be 21% because you subtract 100 from this. So yeah, percent error is 21, which is not too bad. So yeah, it's reasonable, I think. And then the final question is they launch a second projectile with a smaller launch angle. Is the range of the second projectile greater than, less than, or equal to of the original projectile? Well, if the angle is smaller, that means it doesn't it doesn't go up as high in the y direction, meaning it also does not have as much time to stay up in the air. So I would assume that if it was launched again at a smaller launch angle, it would not cover as much a distance as compared to this first launch angle. But yeah, I think that covers all the questions in this FRQ, so yeah.